we want to look at alkenes. What makes an alkene an alkene? Hydrocarbons with a double bond make an alkene called olefins. It's an old common name. The functional group of an alkene is the carbon-carbon double bond, which is reactive as compared to an alkane. Day one, I told you alkanes, very unreactive, no functional group. So this is really about the second functional group of the semester. What do you think the first functional group of the semester has been?
Alkenes.
No, alkanes don't have a functional group.
What?
Think about the word substrate in the last chapter. All these SN1 and SN2 reactions. What do they involve? An alkyl halide. The halide is a functional group. Now we're moving on to the double bond functional group. So double bond is formed by a parallel overlap of p orbitals. Here's a carbon, sp2 hybridized, flat, planar, 120 degrees everywhere. So a lot of books show this, how the electron can move around, forming a pi bond. So here's propane, 3 carbons. So I go 3n plus 2, 6 plus 2, get to 8. Here we have propene, and if I look at all the hydrogens, I get 6. Here's cyclopropane, and I get 6. Here's propyne, and I get 4. So we say this has one element of unsaturation. And an element of saturation can be caused by a double bond or a ring. And here we have 2 elements of saturation. Unsaturation is a structural element that decreases by the number of hydrogens in the molecule by 2. It is also called an index of hydrogen deficiency, which I've never really used that term on any student. Double bonds and rings are elements of unsaturation. So sometimes it's useful to calculate degrees of unsaturation or the number of unsaturations. And so how do you do that? First, find the number of hydrogens the compound would have if the compound was unsaturated. So take the number of carbons you have, multiply it by 2, and add 2 more. That gives you the number of hydrogens you should have. Subtract the number you're looking at in the formula that's in front of you, and then divide that number by 2. And that will give you the number of unsaturations or the degrees of unsaturation. This calculation does not distinguish between whether you have that due to multiple bonds or rings. Both a ring or a double bond lowers the hydrogen count by 2. Now if we have some other atoms than carbon and hydrogen, we call heteroatoms. Halogens replace 1 hydrogen normally. So when we calculate unsaturations, we count the halide as a hydrogen. Oxygen does not change the carbon-hydrogen ratio, so ignore oxygen in the formula. There should be a big asterisk by that. It says not necessarily, but we don't want to go there right now. And we're going to just forget about nitrogen for now. How do we name alkenes? Well, we find LCCC, the longest continuous carbon chain. That includes the double bonded carbon. And then we're going to chop off ane from the alkane and change it to ene. And we number the change so that the double bond has the lowest possible number. In a ring, the double bond is assumed to be between carbons number 1 and carbon number 2. So here we go. 4-carbon chain. Double bond starts at carbon number 1. So I like to call this 1-butene. I like that better than but1-ene. And I guess that's because I'm old. So I like the old IUPAC. There's a 5-carbon chain, double bonds there, 1-pentane. So now the double bond's in a new place. We call this 2-butene or but2-ene. 5-carbon chain, double bonds between carbons 2 and 3. We call this pent2-ene or 2-pentene. Alright, a ring, 6 carbons in the ring, cyclohexene. And presently, We don't have to put any numbers. It's just cyclohexene. So when would we put in numbers? If we have other things going on, like right here. Here we have a methyl group, and we're going to choose this carbon to be number 1 and call this 1-methylcyclopentane. Now notice it's moved a little bit. Now we might have to choose our numbering sequence. We wouldn't want to choose this position to be number 1, because then we'd go 1, 2, 3, 4, 5. We wouldn't want to name this 5-methylcyclopentane. We got to include the double bond between 1 and 2. We want to go counterclockwise around this and name this 3-methylcyclopentane. What if we have more than one double bond? Well, what we're going to do is use these words di, tri, tetra before the ending "ene" to specify how many double bonds we have. So this one will become a favorite one of ours due to 1,2 addition reactions and 1,4 reactions. So we're going to name this 1,3-butadiene. This is 1, 2, 3, 4, 5, 6, 7. A derivative of heptane. So we need to name this hepta-1,3,5-triene. Cyclooctane, 4 double bonds. So cycloocta 1, 3, 5, 7 tetracene. Any questions? Canes as substituents. So here's a double bond and it's bonded to something else. We've got to name this as a substituent. We're going to name this as methylene. CH2, when there's a double bond, becomes a methylene group. Alright, so here I see a 6-carbon ring, cyclohexene, because there's a double bond. And I start numbering here, 1, 2, 3. So 3-methylene cyclohexene. Here is a vinyl group. Don't confuse it with an allylic group, because there's not a carbon here. Now it's probably bonded to a carbon, but what we have attached is just a CH2. We call that a vinyl group. So this becomes 1, 2, 3, 4. Probably don't want to go in that direction. 1, 2, 3. Want to go in that direction. 3-vinyl 1,4-hexadiene. IUPAC would be 3-vinyl hexa 1,5-diene. Cis-trans isomers. So you've been exposed to this already. Here's a 5-carbon chain, and the double bond makes this thing rigid and doesn't rotate. So if I just say 2-pentene or pent-2-ene, you know you have a 5-carbon chain and there's a double bond between the second and third columns. Second and third carbon, what you don't know is the 3D shape. Here we see the chain all on one side of that double bond, or we see the 2 hydrogens on the same side of the double bond. So we call this one cis 2-pentene, or cis-pent-2-ene. Likewise, we call this one trans. These are great true and false to ask this is trans or this is cis, because it's neither. It would be false. So this molecule here doesn't possess cis-trans isomerism. And that is because if you drew it looking the other way, you could flip it around and superimpose it on itself. But the key is when you have 2 groups the same, like these 2 methyl groups on this carbon, that kills any cis-trans isomerism. So we call these geometric isomers. You go back to chapter 5 and look at that big flow chart of isomers. If there are similar groups on the same side of the double bond, with alkene we call it cis. Here's the 2 similar groups, the hydrogens. If they're on opposite side, these 2 hydrogens, we call it trans. And not all cis alkanes are going to have this. You have to have 2 different groups here and 2 different groups here. Since these 2 methyl groups are the same, you don't have cis-trans isomerism. Since these 2 hydrogens are the same, you don't have cis-trans isomerism. So we're going to encounter things that we can't just use cis or trans to give them a name. So we're going to use this thing called the EZ nomenclature, which to me is a pun. But we want to use the Kahn-Ingold pre-log rules. Have you used those before? Don't shake your head no. Shake your head yes.
I don't recognize that name.
That's the RS business. Yes, we use these priority rules. If high priority groups are on the same side of the double bond, the name is Z for, anybody speak German? How do you pronounce this? Sounds real good. And this on opposite sides. So the way I try and remember this is I try and muster up some fake German accent and say, if they're on the same side of the double bond, the same side. There's my German accent. Now when I go edit this, the audio will be so disgusting. I yell. Yeah, so Z for same. Say it with a faked German accent. And I hope I don't offend anybody. So here, are we going to call this cis or trans? We got to dispense with that. But since we have two different groups here and two different groups here, we say this molecule possesses a geometric isomerism. It has this property. So here's our Ingold, Hahn, and pre-log rules. We give bromine first priority. We give chlorine second priority due to their weights on the periodic table. Carbon, we're going to give 1, hydrogen 2. And so these high priority groups are on opposite sides, not the same side. So we call this E. So now we can give it a name. Everybody can write down the correct structure. Everybody knows what we're talking about. And we call this E. 1 bromo, 1 chloro, propene. P. Double bond there, methyl group there. Fortunately, we don't have to name this, but we can decide which is the E isomer and which is the Z isomer. So here's a double bond, and this group is different than that group. And this ring, there's this double bonded carbon here, so that makes this group different from this group. So we'd have to assign this carbon higher priority over this one, because this carbon has 2 hydrogens and a carbon connected to it. This one has like 2 oxygens and a carbon connected to it, so this has first priority, second. And then likewise here, we give this higher priority. We give an ethyl higher priority over a methyl. So this is the E isomer, and if this came out the other way around, then over here, the ethyl has higher priority over the methyl. So this is the Z isomer. The higher priority groups are on the same side. And it's good if you laugh, because I'm told if you laugh, you create a neural connection. You're more likely to remember Z. The higher priority groups are on the same side. Alright, the easy method. This ought to be pretty easy right here. Here's a diene, 8 carbon chain. 3 and 5 is where the double bonds are. So this is a octa 3,5 diene. And here's one of the times where it makes sense to use the new IUPAC method, or you're forced to. So this is neither new or old. You got all this other stuff out in front. You put this in to reflect where the double bonds are. So this one, the high priority groups are on the same side. This one, they're on opposite sides. So this is 3Z, 5E, 3 bromo, octa, 3,5 diene. That's going to be enough for today.